So previously, we had talked about the assumptions behind determining the Euler buckling load. These include, let's see, that we have a pinned connection at both ends, that the beam is that the column is perfectly straight, that the load is at the centroid of the cross section, that we're linear elastic, we don't have any yielding. And then talking about twisting, and then our always favorite plane second germane plane and small deflections. So now we're going to tackle those assumptions and how they are dealt with in actual behavior. So one of the assumptions was that the column is perfectly straight. What happens if your column is not perfectly straight? Let's say it already has a little bit of inherent crookedness or deflection, right? Like a little bit of deflection already. That's your initial mid-span deflection. So when you're looking at the mid-span, not only do you have your axial load P, but now you have a moment P times delta naught. In a perfect world, this is our bifurcation point, right? You have the additional stresses, right? Moment causes additional stresses. We have some compression on this side. And tension on this side due to that moment. So if we already are starting at not from zero, we're going to maybe buckle the compression side of your cross section before you buckle the entire cross section. So instead of starting from zero, we're starting from delta naught, and our load versus our deflection is going to look something like that. It'll eventually get there and buckle, but it's not going to take the same path. And that is assuming it's elastic, and we're just starting with some already horizontal deflection. What's really going to happen is those stresses due to the moment are going to cause different behavior, and it's going to go like this. So with the out of crookedness, you might not actually meet that idealized Euler buckling load. Depending on how out of crooked it is. So let's summarize. Let's see. Buckling is not instantaneous, right? If you look at that, the elastic theory curve, instead of going fine, 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 whoops, I buckled, it's going to gradually buckle. So that's almost kind of good, right? There's some warning. Let's see if I can actually write correctly here. Not associated, prior to, sorry, some warning. Right, there's those additional stresses, that's your axial load, that's your stress due to compression, MC over I. Or tension, right? So this, assuming that it's elastic, the elastic theory, it'll approach PE, right? It'll approach your Euler buckling load. Maybe not get there. But if it's really small, you could have some strength, or if it's really big, you might not actually reach that or actually, go away from your load. So that is why in manufacturing there are limits to how crooked a piece can be. So in this case, the assumption of straightness is dealt with in the manufacturing itself. Basically saying, don't make it that crooked, please. So it's not in the design equations, it's in the manufacturing of the structural steel member. Now, if we look at load eccentricity, meaning the load is not at the centroid, we have a similar story to if it was crooked. The more it deflects, or actually we have the further away it is, right, we have a moment causes a moment, which leads to additional stresses. This, if we follow the elastic theory, will eventually catch up or come close. But depending on how eccentric that is, how but I finished writing the word theory. Depending on how eccentric that load is, causes more moment. More moment means more additional compressive stresses, so you might reach yield a lot sooner, so you're going to have some inelastic behavior. Versus if it was just a small eccentricity, it'll eventually reach it. It'll just have a little bit of warning prior to reaching the buckling load. So again, buckling is not instantaneous. We're going to have some warning. We're going to have additional stresses due to the bending of the column, right? That moment. That moment is equal to your load times the eccentricity. Assuming it's elastic, we'll eventually approach the Euler buckling load. But since it might be substantial, if we have a really large enough E, we could reach yielding, and that would result in loss of strength, significant loss of strength. If the moment is significant, it must be designed, the member must be designed as a member subjected to combined loads, being axial and moment. So let's hope our loads are perfectly where they should be. So that was, we have making sure they're straight. Hopefully we're not designing for combined loads. Now, talking about the end connections. Euler buckling assumes, right? To remind ourselves, Euler buckling assumes pinned connections. So what happens if it is, instead of pinned, it's now fixed, right? Here we have a fixed connection. We're going to do something called a K factor, where we change the length associated with our, we make an effective length, right? So let's say we take something that's pin and calculate the load at which it buckles. Instead, we'll take something that's fixed, and apply an axial load, and then see how that load is compared to the Euler load. And what they find out, right, if this is my pin for my Euler, PE, pin, a fixed column that's fixed will buckle at a load that is 4 times larger than the Euler buckling load. Load strength 4 times as large. If I take that 4 and I put it down in the denominator, I find a K factor of 0.5. Right? That means if you kind of look at this, this would be the shape of an Euler buckling. This would be the shape of a pin column at its Euler buckling load. It's kind of like what's that called? A point of integration. What's that called? Inflection. A point of inflection, right? Where it changes from this to that. So this would be K over 2. Or L over 2 of this entire length. So this would be, alright, if this is 1/2 L, 1/4 L, 1/4 L. What that's saying is I have the same shape, right, as my pin buckling column happening over half the length, but it's not, that is what happens when it buckles. That makes sense. So my effective length, if I have fixed end conditions, is 1/2. I only have to think of half the length. God, I keep saying beam. A column that's 30 feet long with fixed ends will buckle. Let's see, maybe let's write that down. A 30-foot column with fixed ends will buckle at the same load as a 15-foot column pin ends. So if you make your ends fix, you can have a higher load strength for the same height column. Or if you have fix, you can make a longer column for the same load strength. So we come up with this concept of an effective length factor. And it is associated with what the ratio of the length that we can find the pin shape, buckled shape. So our effective length, KL, might also be called LE or LC. LC. Okay, I'm gonna erase that. It's the length of your equivalent pin-ended column with similar elastic buckling load. Right? Like I said, a 30-foot column with fixed will buckle at the same load as a 15-inch column with pin. And it is the distance between the points of inflection at your buckled shape. Right. These are your points of inflection. So what they did was they went and measured effective lengths for a few different end conditions. This first one, this is our fix, right? Rotation fixed, translation fixed. A is fix. And you can see, right? There's your pin. 0.5 times your L. That's your pin buckled shape. If you look at, this is pin on top, number B, or letter B, pin fixed on the bottom. Okay, that's the same, and then there's a point of inflection, like right here. So this distance is 0.7 of the whole length of that column. A, where it changes, the points of inflection is half the length of the column. B is 0.7. C, it's actually, right, this is, you can kind of tell this is half, this is half of it, half of your buckled shape. This is the other half of your buckled shape. Maybe if you drew it back, right, there's your other half. So that's why it's 1, because it's half your buckled shape and the other half of your buckled shape for your pinned end. Right, that's half, and then that's half. So half plus half is 1, that's why it's 1. And then here's your pin. That's your traditional Euler buckling load. So it's 1. E is what? Fixed, free. Bottom is fixed, top is free, and you'll see that is like half of your Euler buckling shape. So really, to get the full Euler buckling shape, you have to do another half like that. So it's actually 2. So having something that's fixed free, you can only have half as much length. Yeah. You need 2 lengths of it to right, this is half. So here's the other half. Need 2 column lengths to get your pin shape. So that's why it's 2. And the same thing happens with your pin free. Right, the other half would be up there somewhere. Same story. You need 2 column lengths to get your pin shape. So your effective length value is 2. Remind ourselves that pin is our Euler assumption. Right, pin is our Euler assumption. So to account for our Euler assumption that it's pin, we use an effective length factor to change our length for different end conditions. To change the length that we use for determining our buckling load, we use the effective length factor. So our next assumption from Euler buckling is that the cross-section is linear elastic and stays linear elastic, nothing yields. So, but we talked about residual stresses causing yielding to occur. So we're going to talk about inelastic material effects, which occur when your stress at any point at any part of cross-section part exceeds your yield stress. So let's say due to residual stresses, we start yielding at a lower point than our yield stress, right? Because of that residual stress, meaning we're not starting at zero. And because of that, this is just like that thing we drew earlier. We're going to have a curve more like that rather than straight up elastic plastic. And we can calculate a tangent modulus, which is the elastic modulus associated with that curve. So it's tangent to the curve. So if this curve right here is our Euler buckling curve, if we look at, this is a chart, a graph of our slenderness ratio and our stress in our cross section. If we have Euler buckling where we never reach yielding, or we never reach yielding any part of the cross section, we follow that blue curve and we can calculate our stress according to that equation. Now notice we put the K in there, we're making our slenderness ratio include our effective length factor. However, once any part of the cross section begins to yield, we have different behavior, and eventually the entire cross section yields. I can break this up by the stresses below this point are associated with elastic buckling, and above this point and this point right here is Fy minus your residual stresses. Those residual stresses mean I'm going to begin yielding, which is causing inelastic buckling. I'm going to have yielding somewhere within the cross section, likely beginning at the flange tips. And in order to calculate that inelastic buckling curve, I use my tangent elastic modulus. So I'm going to break this up into two classes of buckling. Elastic buckling, no yielding prior to buckling. Your tangent modulus is equal to your elastic modulus because you're staying elastic. Your stress associated with buckling is less than or equal to your yield stress minus your maximum residual stress. And that stress, that FE, that stress, predicts buckling and is associated with Euler buckling. So that's inelastic buckling. That's elastic buckling. Inelastic buckling means that there is some yielding prior to buckling, so loss of stiffness. That's why we have that tangent modulus, because we're decreasing our stiffness. Our stress at buckling is greater than our yield stress minus the residual stress. And we're going to define the stress associated with buckling as FC. FE predicts elastic buckling. FE predicts elastic buckling, and FC predicts inelastic buckling. If we're going to look at our overall column strength, again looking at our slenderness ratio and our stress, here's some experimental data. This is our overall column strength, so we're looking at all of the assumptions versus actual behavior. We have and this is where my behavior begins to change, right? So let's say we're breaking it about right here. This is my inelastic curve and my elastic curve. So let's see, if I have a low stiffness ratio, KL over R, I'm down in, I'm over here, low, right? Then I'm more likely to be governed by inelastic buckling. If I have a high KL over R, so if I'm high, that means if I'm very slender, long and skinny, high KL over R, I'm more likely to be governed, I'm going to more likely to be inelastic buckling, and I'm governed by out of straightness effects. So in this area, out of straightness is going to lead to buckling sooner rather than later. In this area, inelastic material effects including residual stresses. Which kind of makes sense, right? The higher stiffness ratio, you're long and skinny, you're gonna buckle. You're more likely to buckle before you yield. A lower stiffness ratio, you're more likely to yield the whole, or almost the whole cross section before you buckle. So you're gonna be inelastic. And because of that high KL over R, you're going to care more about whether or not you have those out of straightness effects that's causing additional moment and causing additional stress versus if it's shorter and fatter, you really care more about the fact that you're yielding first before you buckle. So this is just the overall column strength. That's our experimental data that has been gathered by our colleagues in academia and in industry, and we've gathered all of our information and combined it and put it into our steel manual. So to summarize, the major factors determining strength is your slenderness, and your end restraint, so that we've taken into account using our effective length of K factors. Then there's also some initial crookedness or low eccentricity, and there's yielding, prior yielding or residual stresses within the cross section that'll affect when something yields. The latter two are highly variable between specimens. So that's just something that you got to put in there in our phi factors when we're calculating you know, how when we're calculating our strength, we have our phi factors, which reduce our nominal strength, and that's how we account for things that are highly variable. Or with the initial crookedness, right, that's taken care of hopefully at the manufacturing level. So when we're looking at our manual, these are the two that we're going to look at the most, that we can control. As designers, we can control how long something is, what shape we use, governing its radius of gyration, and we can control our end restraints, our K factors. We can't control the last two things. We have less control over them. So when we're doing our design, we look at our slenderness ratio and our end restraints. So that is the end of how we account for the assumptions of Euler buckling.